Hello, friend. Welcome to a place where time moves slowly, where curiosity breathes softly, and where the greatest mysteries aren't solved, just softly wondered about. Tonight, we're going somewhere unusual, somewhere before light, before sound, before anything you could touch or name, before the first star ignited, before atoms learned to dance, before time itself had anywhere to go. We're drifting back to a moment that wasn't a moment at all, because moments hadn't been invented yet. A place scientists call before the Big Bang, though even that phrase feels too confident, too certain, for something so strange and unreachable. What was there? Was there even a there? And if nothing existed, how did everything begin? These aren't questions with tidy answers, but they're the kind of questions that make the universe feel wider, older, and somehow closer. Before we drift into this quiet mystery together, if you find peace in these slow journeys through wonder, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. Imagine you're standing in a room with no walls, no floor beneath your feet, no ceiling above, no light, no darkness, because darkness needs space to fill, and there is no space yet. No temperature, because temperature needs particles to vibrate, and particles haven't arrived. No silence, because silence needs emptiness to echo through, and even emptiness doesn't exist. This is what scientists believe came before our universe, not a void, not a blank canvas, something stranger, the absence of absence itself. Physicists call this state quantum nothingness. But don't let the name fool you. It wasn't peaceful. It wasn't still. Some researchers suggest it was seething, flickering with possibility, trembling at the edge of something about to be born. Stephen Hawking once said that asking what came before the Big Bang might be like asking what's north of the North Pole. The question itself might not make sense, because time as we know it, time that flows from past to future, didn't exist yet. There was no before to speak of. And yet, our minds keep reaching back, keep wondering. Because wondering is what minds do, even when the answer lives beyond the edge of language. Let's step carefully into what we do know, or rather, what the equations whisper. Around 13.8 billion years ago, our universe began. Not in a place, but as a place. Not at a time, but as time. Everything that would become galaxies and stars and oceans and you was compressed into something unimaginably small. Some scientists suggest it was smaller than a single atom. Others say it might have been a point with no size at all, what mathematicians call a singularity. Temperature, infinite. Density, beyond comprehension. The laws of physics as we know them, gravity, electromagnetism, the forces that hold atoms together, they didn't apply yet. They were still waiting to be written. And then, in less than a trillionth of a second, everything exploded outward, not into space, but as space itself, unfolding like a breath held too long, finally released. This is the moment we call the Big Bang. Though it wasn't really a bang, there was no sound, no ears to hear it. Just an eruption of existence, sudden and silent and impossible to imagine. But here's where it gets stranger. That moment, the very first moment, still lives inside everything. Inside the light from distant stars. Inside the atoms in your body. Inside the air you're breathing right now. You are made of the Big Bang. You are the universe, remembering itself. So, what sparked it? What set the clock ticking? What whispered begin? One of the most beautiful ideas comes from quantum mechanics, the strange science of the very small. At the tiniest scales, reality doesn't behave the way we expect. particles flicker in and out of existence. Energy borrows itself from nothing, then pays itself back a moment later. The universe, it seems, is allowed to be uncertain. Some physicists believe that the Big Bang might have been a quantum fluctuation, a cosmic accident, if you will, a moment when energy borrowed itself from nothingness, and instead of vanishing again, it expanded. It became real. It became everything. It's a wild thought that the entire universe, every planet, every person, every thought you've ever had, might have started as a glitch in the fabric of nothing. And yet, the math holds. The equations don't flinch. They say it's possible. They say it might have happened exactly that way. But there's another idea, quieter and more mysterious. Some scientists suggest that our universe might not be alone, that before the Big Bang, there might have been other universes, whole realities that expanded, aged, and collapsed back into nothingness. And from the ashes of one of those fallen universes, ours was born. This is sometimes called the cyclic universe model. It suggests that time doesn't have a beginning or an end. It breathes. Expansion, collapse, expansion again. Like a heartbeat that never stops. Each universe gives birth to the next, endlessly. In this view, the Big Bang wasn't the first moment, just our moment, the start of this chapter, not the start of the story. There's something oddly comforting about that idea, isn't there? The thought that existence doesn't begin or end, it just changes form. That the universe is ancient beyond ancient, and every ending is just a different kind of beginning. Then there's the multiverse, a term that sounds like science fiction but is taken seriously by many physicists today. According to some theories, the Big Bang might not have created one universe. It might have created countless universes, all of them branching off from the same initial moment, each one slightly different, each one with its own laws of physics, its own arrangement of matter, its own story. In one universe, gravity might be stronger, causing stars to burn out faster. In another, atoms might not hold together at all, leaving only formless energy. And in this universe, ours, the conditions just happen to be right for galaxies to form, for planets to cool, for life to emerge. It's called the inflationary multiverse hypothesis. The idea is that the same process that caused our universe to expand, called cosmic inflation, didn't stop. It kept going, budding off new universes like bubbles in boiling water. Each bubble is its own reality, forever separated from the others. We can't see them. We can't reach them. They exist beyond the edge of everything we could ever observe. But mathematically, they might be just as real as the ground beneath your feet. It makes you wonder, doesn't it? If infinite universes exist, and in some of them the laws of physics are just slightly different, then maybe, in at least one of them, you're hearing this exact sentence right now, but the stars outside are purple instead of white. But let's come back to silence for a moment, to the thing we can't quite name. The great mystery isn't just what started the Big Bang, it's why there's something instead of nothing. Why does existence exist at all? Philosophers have asked this question for thousands of years. Leibniz called it the primordial existential question. Why is there a universe? Why are there laws of physics? Why does reality prefer being to not being? Science doesn't have an answer, not yet. Maybe not ever. Some questions might live forever at the edge of knowability, not because we're not smart enough, but because the question itself is woven into the fabric of existence in a way we can't step outside of to examine. And maybe that's okay. Maybe some mysteries are meant to stay mysterious, not because we give up, but because the wondering itself is part of what makes us human. Here's something that might surprise you. The Big Bang left behind evidence, a kind of cosmic fingerprint still visible today. In 1964, two scientists named Arno Penzias and Robert Wilson were working with a large radio antenna in New Jersey, trying to detect faint signals from space. But no matter what they did, they kept hearing a soft hiss, a static that wouldn't go away. At first, they thought it was interference, maybe pigeons nesting in the antenna. But even after cleaning everything, the hiss remained. Eventually, they realized what they were hearing: the leftover glow of the Big Bang itself, a faint radiation, cooled over billions of years, now just a whisper above absolute zero. Scientists call it the cosmic microwave background radiation, or CMB for short. It's everywhere. In every direction you look, the universe is still softly humming with the echo of its birth. If you've ever seen static on an old TV screen, about 1% of that fuzz is actually radiation from the Big Bang, reaching your eyes after traveling for nearly 14 billion years. You're not just learning about the beginning of the universe, you're bathed in it, every moment. It's still here, touching you gently, like an ancient song that never quite fades. And what about time itself? Did it exist before the Big Bang? Most physicists say no. Time, like space, is part of the universe. It was created along with everything else. Asking what happened before time began is like asking what's north of the North Pole. The question folds in on itself, but some theories suggest otherwise. That time might be more fundamental than we think, that it might flow independently, and the Big Bang was just an event within time, not the start of it. One theory, called loop quantum gravity, suggests that time has always existed, and our universe might have emerged from the collapse of a previous one. In this view, the Big Bang was actually a big bounce, the moment when a dying universe rebounded into a new one. It's a humbling thought, isn't it? That time might be older than existence itself, that before the stars, before the atoms, before light and sound and substance, there was still the quiet, patient ticking of time, waiting for something to measure. So, where does that leave us? Here, now. In a universe that somehow decided to exist, made of particles that once didn't exist, experiencing time that might not have always flowed, wondering about a beginning that might not have been a beginning at all. And isn't that the strangest gift? That we, collections of atoms that were once unimaginably hot and compressed, can look back across 13.8 billion years and ask, how did this start? Why are we here? The universe is not only strange, it's aware of its own strangeness through us. You are the universe, looking back at itself, trying to remember, trying to understand. And maybe the answer isn't as important as the looking. We've only just begun. Ahead, there are more mysteries waiting. Questions about what the universe was like in its very first seconds, how the first atoms formed, and why the darkness between stars isn't actually empty at all. But for now, let that settle. Let the strangeness of it sink in softly, the way moonlight sinks into water. You don't need to hold it tightly. Just let it rest beside you. There's more to explore. Just ahead. The universe was born, but it wasn't ready yet. In those first moments, the first trillionth of a second, everything that would ever exist was there, compressed into a space smaller than the period at the end of this sentence. But it wasn't stars, it wasn't planets, it wasn't even atoms. It was pure energy, unimaginably hot, unimaginably dense. A kind of primordial soup that physics barely knows how to describe. This wasn't a place you could visit. It wasn't a place at all. It was a condition, a state of being so extreme that matter as we know it couldn't exist yet. Only energy, seething and expanding, racing outward faster than anything would ever move again. Scientists call this the Planck epoch, the very first moment. And it lasted less time than it takes light to cross the width of a single atom. What happened in that impossible instant? How did the universe go from pure chaos to the ordered, structured reality we see today? Let's drift into the first second of existence, slowly, carefully. Because in that single second, everything changed. At the very beginning, temperature ruled everything. In the first fraction of a second, the universe was about 10 trillion degrees Celsius. That's hotter than the core of the largest stars, hotter than anything that exists in the universe today. At that temperature, even the fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, were unified into a single force. Physicists believe that in this state, the universe was perfectly symmetrical. There were no distinctions yet, no differences, just pure, undifferentiated energy, existing in a kind of cosmic oneness. But symmetry is fragile, and as the universe expanded, it cooled. And as it cooled, something extraordinary happened. The forces began to separate. First, gravity split off. Then the strong nuclear force. Then the weak force and electromagnetism. Each separation released energy, like ice cracking as water freezes. And with each crack, the universe became more complex, more interesting, more capable of creating structure. It's called spontaneous symmetry breaking. And it sounds technical, but it's really just a story about how sameness becomes difference, how unity becomes diversity, how a universe with no features at all begins to develop personality. Without those separations, atoms couldn't form, stars couldn't ignite, you couldn't exist. The act of cooling, of losing that original perfection, is what made everything possible. By 1 microsecond after the Big Bang, the universe had cooled enough for quarks to appear. Quarks are the building blocks of matter, smaller than atoms, smaller than protons and neutrons. They're among the most fundamental pieces of reality we know. And in that first microsecond, they swam freely in a hot plasma, colliding and bouncing off each other, too energetic to stick together. Physicists call this state the quark-gluon plasma. It's a bit like a cosmic soup, thick and roiling, where particles that will one day make up everything, every mountain, every ocean, every living cell, are just beginning to take shape. But they're not ready yet. It's still too hot. The quarks are restless, wild, unbound. Then, around 1 microsecond in, the temperature dropped just enough, and the quarks began to lock together, 3 at a time, forming protons and neutrons. This moment, called the quark epoch, is when matter as we know it truly began. Before this, there were only fragments, energy pretending to be particles. After this, there were stable building blocks, the ingredients for atoms, the ingredients for everything, and all of this happened in less time than it takes you to blink. By the time the universe was 1 second old, it was already a vastly different place. The temperature had dropped to about 10 billion degrees, still unimaginably hot, but cool enough for something new to emerge: light. Before this moment, light couldn't travel freely. The universe was so dense, so packed with particles, that photons, the particles of light, would collide with electrons and scatter almost immediately. It was like trying to see through thick fog. Light existed, but it couldn't go anywhere. Physicists call this the opaque era. The universe was dark, not because there was no light, but because light couldn't escape. It was trapped, bouncing endlessly in the chaos. This would continue for hundreds of thousands of years. But already, in that first second, the seeds of transparency were being planted. The universe was expanding. The fog was thinning. Light was patient. Around 3 minutes after the Big Bang, something critical happened. The first atomic nuclei formed. Up until this point, protons and neutrons had been crashing into each other randomly, too hot and fast to stick together. But as the temperature continued to drop, they began to fuse. 2 protons and 2 neutrons combined to form helium nuclei. Some protons stayed alone, as hydrogen nuclei. This process is called Big Bang nucleosynthesis, and it lasted only about 17 minutes. In those 17 minutes, the universe created about 75% hydrogen and 25% helium, the same ratio we still see in the universe today, billions of years later. Almost no heavier elements formed yet. No carbon, no oxygen, no iron. Those would come much later, inside stars. But hydrogen and helium, they were born in the fire of the Big Bang itself. Here's the beautiful part. Every hydrogen atom in your body, every single one, was created in those first few minutes. The hydrogen in the water you drink, the hydrogen in your cells, the hydrogen in the oceans, it's all 13.8 billion years old. You are made of the universe's first breath. For the next 380,000 years, the universe continued to expand and cool, but it was still opaque, still dark. Light still couldn't travel freely. Then, around 380,000 years after the Big Bang, the temperature finally dropped to about 3,000 degrees Celsius, cool enough for electrons to slow down and bind with atomic nuclei. This moment is called recombination, and it changed everything. Before recombination, the universe was a plasma, electrons zipping around freely, colliding with photons, scattering light in every direction. But once electrons settled into orbit around nuclei, forming the first complete atoms, photons could finally travel without interruption. For the first time, light could move freely through space. Astronomers call this the moment the universe became transparent. And the light that was released in that moment, the first light to ever travel unobstructed, is still traveling today. It's the cosmic microwave background radiation we talked about earlier. The afterglow of creation, cooled over billions of years, now just a faint whisper. But it's still here, still reaching us. A photograph of the universe when it was just 380,000 years old, frozen in time, waiting to be seen. When scientists measure that ancient light, they're not just looking back in time, they're seeing the moment the universe opened its eyes. But here's something most people don't realize. The early universe wasn't perfectly smooth. If you look closely at the cosmic microwave background, you'll see tiny variations, little fluctuations in temperature, barely 100,000th of a degree different from one spot to another. Those tiny ripples might not seem like much, but they're the reason galaxies exist, the reason stars formed, the reason you're here. Scientists believe these fluctuations came from quantum irregularities in the very first moments after the Big Bang, random, microscopic differences in density that got stretched and amplified as the universe expanded. In regions where the density was slightly higher, gravity pulled a little harder. Matter began to clump together. Over millions of years, those clumps grew larger, pulling in more matter, until eventually they collapsed into the first stars and galaxies. Without those tiny imperfections, the universe would have stayed smooth, uniform, lifeless. But because reality allowed for a little messiness, for a little chaos, structure emerged, complexity emerged, life emerged. Perfection would have been boring. It was the flaws that made everything beautiful. Let's pause here and think about time for a moment. We talk about the first second and the first 3 minutes as if time was ticking normally, but time itself was different back then. According to Einstein's theory of relativity, time isn't absolute. It flows differently depending on gravity and speed. And in the early universe, where everything was compressed and moving so fast, time behaved strangely. From our perspective, looking back, it seems like the universe aged normally, 1 second after another. But if you could somehow have been there, experiencing it from the inside, time might have felt stretched, distorted, almost fluid. Some physicists even suggest that in the very first moments, time might not have been linear at all. It might have been looped, tangled, woven into space in ways we can't quite picture. Time, it turns out, is as much a mystery as the Big Bang itself. We measure it, we feel it pass, we structure our lives around it, but we still don't fully understand what it is or why it flows in only one direction. The universe wasn't just born into time. Time was born into the universe. And maybe that's the most extraordinary thing of all. By the end of the first second, the universe was already 100 light years across. 1 second. And already larger than the distance light could travel in a human lifetime. By the end of the first minute, it was millions of light years across. Expanding so fast that no signal, no information, no force could keep up. Space-time itself was stretching, pulling galaxies apart faster than gravity could hold them together. And it hasn't stopped. The universe is still expanding today, faster and faster, accelerating into the void. Scientists discovered this in 1998, and it shocked everyone. They expected the universe's expansion to be slowing down, pulled back by gravity. But instead, something is pushing it outward, faster and faster. They call this mysterious force dark energy, and it makes up about 68% of the universe. We don't know what it is. We can't see it. We can only see its effects, the way it stretches space-time, pushing galaxies away from each other at ever-increasing speeds. Some physicists believe dark energy is a property of space itself, that empty space has a kind of pressure, an inherent tendency to expand. Others think it might be a new kind of field filling the universe, driving its growth. But no one really knows. Dark energy is one of the great unsolved mysteries of cosmology. And it's winning. The universe is being pulled apart by something invisible. And we're still trying to figure out what it is. So in those first moments, those first seconds, minutes, hours, the universe went from a single point of infinite density to a vast, expanding cosmos filled with energy, matter, and light. It cooled, it separated, it became complex. And somewhere in that complexity, the seeds of stars were planted, the seeds of planets, the seeds of life, all of it unfolding in silence. No one there to witness it, no eyes to see, no minds to wonder, just the universe becoming itself. And yet, here we are, billions of years later, made of atoms forged in those first moments, existing because the universe was just imperfect enough, just chaotic enough, just patient enough to allow for something like us. You are the universe's way of looking back at its own beginning, of trying to remember, of asking quietly in the dark, how did I get here? But the story doesn't end with light and atoms. Something else was waiting in the darkness, something that would shape the universe in ways no one expected, until we finally learned to see it. Let's drift deeper. The universe was full of light, full of atoms, full of possibility. But there was something else, something invisible, something that didn't interact with light, didn't leave traces, didn't announce itself in any way we could directly observe. And yet, it was everywhere, holding galaxies together, bending space-time, shaping the architecture of everything we see. Scientists call it dark matter, and it makes up about 85% of all the matter in the universe. Think about that for a moment. Everything you've ever seen, every star, every planet, every grain of sand, every human being, is made of what we call ordinary matter. Protons, neutrons, electrons, the stuff that interacts with light, that we can touch and measure. But that only accounts for 15% of the matter in the cosmos. The rest, hidden, silent, invisible. We only know it's there because of the way it pulls on the things we can see. The story of dark matter begins with a woman named Vera Rubin. In the 1970s, Rubin was studying spiral galaxies, those beautiful spinning disks of stars like cosmic whirlpools. She wanted to understand how fast stars were moving as they orbited the galaxy's center. According to the laws of physics, stars farther from the center should move slower, just like planets farther from the sun take longer to complete their orbits. The gravity from the visible matter in the galaxy should weaken with distance, and the stars should slow down accordingly. But that's not what Rubin found. Instead, she discovered that stars on the outer edges of galaxies were moving just as fast as stars near the center, sometimes even faster, as if something invisible was pulling on them, holding them in place, keeping them from flying off into space. At first, people didn't believe her. The data seemed wrong, impossible. But Rubin kept measuring, kept observing, kept checking her work. And every galaxy she studied showed the same pattern. The conclusion was unavoidable. There must be more mass in these galaxies than we can see. A lot more. Enough to account for the gravitational pull needed to keep those outer stars moving so fast. Dark matter wasn't just a theory anymore. It was a necessity. The math demanded it. The universe insisted on it. And Vera Rubin, quietly and persistently, showed us that most of the universe was hiding in plain sight. So, what is dark matter made of? That's the question physicists have been trying to answer for decades, and the truth is, we still don't know. It's not made of atoms, at least not the kind we're familiar with. It doesn't emit light, doesn't absorb light, doesn't reflect light. It passes through ordinary matter, like a ghost. You could have dark matter particles moving through your body right now, and you'd never feel a thing. Some scientists believe dark matter is made of particles called WIMPs, weakly interacting massive particles. These would be heavier than protons, but almost impossible to detect, because they barely interact with anything. Others think it might be made of axions, tiny, nearly massless particles that were predicted by theoretical physics, but have never been observed directly. There are even more exotic ideas. Some researchers suggest dark matter could be primordial black holes, tiny black holes formed in the first moments after the Big Bang, too small to swallow stars, but massive enough to bend space-time. And then there's the possibility that dark matter isn't a particle at all, that maybe we've been thinking about gravity wrong this whole time, and what we're seeing isn't invisible matter. It's a correction to Einstein's equations that we haven't discovered yet. But most physicists believe dark matter is real, that it's out there, everywhere, invisible but essential, and that one day we'll figure out what it is. Here's where it gets stranger. Dark matter doesn't just exist. It's woven into the structure of the universe itself. In the early universe, after atoms formed and light was set free, dark matter was already there, quietly clumping together under the pull of its own gravity. It couldn't shine, couldn't radiate heat, couldn't lose energy the way ordinary matter does. So it just kept collapsing, forming vast, invisible structures. Scientists call these structures the cosmic web. If you could see dark matter, you'd see threads stretching across billions of light years, connecting galaxies like neurons in a brain. Between the threads are enormous voids, vast stretches of nearly empty space. Ordinary matter, the stuff that makes stars and planets, fell into the gravitational wells created by dark matter, like water flowing into valleys carved by invisible rivers. Without dark matter, galaxies wouldn't have formed, stars wouldn't have ignited, planets wouldn't have coalesced. The universe would be a cold, diffuse fog of hydrogen and helium, drifting endlessly with no structure, no complexity, no life. Dark matter is the skeleton of the cosmos, invisible, silent, essential. We are decorations on a framework we cannot see. Let's talk about one of the strangest experiments ever attempted. Deep underground, buried beneath mountains to shield them from cosmic rays, scientists have built detectors designed to catch dark matter particles. These detectors are filled with ultra-pure substances, liquid xenon, supercooled silicon, even tanks of argon gas, kept at temperatures near absolute zero. The idea is that if a dark matter particle passes through and happens to collide with an atom, it will produce a tiny flash of light or a faint vibration that the detector can measure. So far, after decades of searching, we haven't caught one. Not a single confirmed detection. Not one flash that couldn't be explained by something else. The dark matter particles, if they exist, are slipping through these detectors without leaving a trace. And yet, physicists keep trying, building more sensitive instruments, going deeper underground, waiting patiently in the dark, hoping for a signal that will finally reveal what dark matter is made of. It's an act of faith in a way, a belief that the universe can be understood, even when it hides its secrets so well. Some experiments have reported faint hints, tiny anomalies that could be dark matter or could be nothing, but nothing confirmed, nothing certain. The universe, it seems, isn't ready to give up its ghosts just yet. But here's the thing. Even though we can't see dark matter directly, we can see its effects everywhere we look. One of the most striking examples is something called gravitational lensing. According to Einstein's theory of general relativity, massive objects bend space-time. Light traveling through space follows those curves like a marble rolling along the surface of a stretched rubber sheet. When light from a distant galaxy passes by a cluster of dark matter, the dark matter's gravity bends that light, distorting the image. Sometimes the light is stretched into arcs. Sometimes it's multiplied, creating multiple images of the same galaxy. Sometimes it's magnified, allowing us to see galaxies that would otherwise be too faint to detect. Astronomers use these distortions as a kind of map. By measuring how light bends, they can trace the invisible mass causing the bending. And what they find, again and again, is that there's far more mass there than we can see with telescopes. It's like watching footprints appear in sand. Even though you can't see the person walking, the effect is undeniable. The cause remains hidden. In 2006, astronomers observed a collision between two galaxy clusters, called the Bullet Cluster. When the clusters smashed together, the ordinary matter, mostly hot gas, slowed down and clumped in the middle, glowing brightly in X-rays. But the dark matter? It passed right through like two clouds of smoke drifting past each other. Using gravitational lensing, scientists could see that most of the mass was no longer where the visible matter was. It had separated, continuing onward as if nothing had happened. It was one of the strongest pieces of evidence we have that dark matter is real, that it's not just a mistake in our equations, that it truly exists, independent of ordinary matter, shaping the universe in ways we're only beginning to understand. Now, you might be wondering, if dark matter is everywhere, why don't we feel it? The answer is scale. Dark matter interacts with gravity, but gravity is an incredibly weak force on small scales. You'd need an enormous amount of dark matter concentrated in one place to feel its pull. On the scale of a galaxy, dark matter dominates. It's what holds the stars in orbit, what keeps the galaxy from flying apart. But on the scale of a planet or a human body, its effect is negligible. There might be dark matter particles passing through you right now, thousands of them every second, but they're so weakly interacting that they slip through the atoms in your body without touching anything. No collisions, no interactions, just silent passage. It's humbling, isn't it? To know that most of the universe is made of something we can't touch, can't see, can't even detect, except through the faintest gravitational whispers. And yet, here we are, made of the rare 15%, the matter that decided to light up, to interact, to become visible. The exception, not the rule. Maybe that's why existence feels so fragile, so precious. We're the minority, the anomaly, the part of the universe that learned to shine. There's a theory, still speculative, still unproven, that dark matter might not be completely invisible after all. Some physicists believe that dark matter particles could occasionally collide with each other and annihilate, releasing energy in the form of gamma rays or other radiation. If that's true, then deep space telescopes might be able to detect a faint glow from regions where dark matter is densest. In 2014, scientists using the Fermi Gamma Ray Space Telescope detected an unexpected signal coming from the center of the Milky Way, a soft glow that didn't match any known source. Some researchers suggested it could be dark matter annihilation. Others argued it was just the combined light of ancient stars or pulsars. The debate continues. The signal is real, but its source remains uncertain. Another mystery layered on top of a mystery. That's how science often works, not with sudden revelations, but with slow accumulations of evidence. Questions that lead to more questions. Hints that take decades to confirm or dismiss. Dark matter is patient, and so are the scientists trying to understand it. Let's step back and think about what this means. The universe is not what it appears to be. Most of it is hidden. Most of it is silent. We walk through a cosmos where the majority of existence is invisible, and we only know it's there because of the way it pulls on the things we can see. It's a bit like trying to understand a conversation by only hearing every fifth word. You can tell something is being said. You can sense the shape of the meaning, but the full story remains just out of reach. And maybe that's okay. Maybe not knowing everything is part of what makes the universe so compelling. There's still room for discovery, still room for wonder, still vast territories of reality waiting to be explored. We've mapped less than 5% of the universe in any meaningful way. The rest, dark matter, dark energy, the countless galaxies beyond our observation, remains a frontier. You're not just living in a universe, you're living in a mystery. And every time you look up at the stars, you're seeing only the brightest hints of something far deeper, far stranger, far more intricate than we've yet imagined. Dark matter shaped the early universe. It guided the formation of galaxies. It created the conditions for stars to be born, for planets to form, for life to emerge. Without it, none of this would be here. Not the Milky Way, not the Sun, not Earth, not you. And yet, it asks for nothing in return. It doesn't shine. It doesn't announce itself. It simply exists, quietly holding everything together, invisible but indispensable. There's something almost poetic about that, don't you think? The idea that the universe's greatest influence is also its quietest, that what we see is only possible because of what we cannot see. Maybe that's a lesson worth carrying softly into sleep, that not everything needs to be visible to matter. That presence doesn't require proof, that the most important things, gravity, love, memory, meaning, are often the ones we feel rather than see. The invisible framework that holds galaxies together also holds the story of what came next. Because dark matter didn't just shape space, it shaped time. It determined when and where the first stars would ignite, lighting up the cosmos after hundreds of millions of years of darkness. And those first stars, they changed everything. For hundreds of millions of years, the universe was dark, not the comfortable darkness of night, where stars shine and the moon glows softly, but true darkness, empty, silent, a vast ocean of hydrogen and helium, drifting in the cold, waiting for something to happen. Astronomers call this the cosmic dark ages, and it lasted longer than you might think, somewhere between 100 and 400 million years after the Big Bang. No stars, no galaxies, no light except the fading afterglow of the Big Bang itself, stretched and cooled into invisibility. But beneath that darkness, something was stirring. Gravity was pulling. Dark matter was guiding. And slowly, quietly, the first stars began to form. When they finally ignited, they didn't just light up the universe. They transformed it. They created elements that didn't exist before. They set in motion everything that would follow: galaxies, planets, life itself. The first stars were not like the sun. They were monsters, and their brief, violent lives changed the cosmos forever. Imagine a cloud of hydrogen, vast and cold, floating in the early universe. At first, it's too diffuse to do much of anything, just a faint wisp, barely denser than the space around it. But gravity is patient, and over millions of years, that cloud begins to collapse. Slowly at first, then faster as the atoms pull each other inward, converging on a single point. As the cloud collapses, it heats up. Pressure builds. Atoms collide more and more violently, their motion and generating heat. And when the temperature at the core reaches about 10 million degrees Celsius, something extraordinary happens. Hydrogen atoms begin to fuse. Two hydrogen nuclei slam together with so much force that they merge, forming helium and releasing energy. That energy pushes outward, resisting the crush of gravity. A balance is struck. The cloud stops collapsing, and a star is born. This is nuclear fusion, the process that powers every star in the universe. The same reaction that lights the sun, that warms your skin on a summer day, that made life on Earth possible. But the first stars, they were different. Bigger, hotter, brighter. Scientists believe the earliest stars were anywhere from 100 to 300 times the mass of our sun. They burned blue-white, fierce and fast, radiating so much energy that they could only live for a few million years before exhausting their fuel. Our sun will shine for about 10 billion years. The first stars lasted a blink in comparison. But in that brief existence, they did something no process in the universe had done before. They created heavy elements. Here's the thing about the early universe. It only had hydrogen, helium, and tiny traces of lithium. That's it. No carbon, no oxygen, no nitrogen, no iron, no calcium. None of the elements that make up planets, oceans, or living cells. The periodic table, as we know it, didn't exist yet. But inside the cores of those first stars, conditions were extreme enough to forge new elements. As hydrogen fused into helium, and helium fused into carbon, and carbon into oxygen, the star worked its way up the periodic table. Each fusion reaction released energy, keeping the star alive, pushing back against gravity's inward pull. But fusion can't go on forever. There's a limit. When the core of a massive star starts fusing iron, something changes. Iron doesn't release energy when it fuses. It absorbs it. Suddenly, the star loses the outward pressure that's been holding it up. Gravity wins. In less than a second, the core collapses. The outer layers fall inward at nearly a quarter of the speed of light, and when they hit the core, they rebound in a catastrophic explosion, a supernova. For a few weeks, a single exploding star can shine as brightly as an entire galaxy. And in that explosion, elements heavier than iron, gold, silver, uranium, are forged in the heat and chaos, then scattered into space. The first stars didn't just light up the universe, they seeded it. They spread the raw materials for planets, for oceans, for life, across the cosmos. Every atom in your body heavier than hydrogen was made inside a star. You are, quite literally, stardust. Not as a metaphor, but as a fact. The first stars also did something else. They began to clear the fog. Remember, the universe had been opaque for hundreds of millions of years. Even after atoms formed and light could travel freely, the hydrogen gas filling space was neutral. It didn't interact much with light. The universe was transparent, yes, but still dark. No sources of light yet, nothing to see. But when the first stars ignited, their ultraviolet radiation was so intense that it began to strip electrons off the surrounding hydrogen atoms, ionizing them. This process is called reionization. and it fundamentally changed the nature of space. Ionized hydrogen is different. It's electrically charged, reactive, capable of interacting with light in new ways. As more and more stars formed, they created bubbles of ionized gas around them, like candles lighting up a dark room one by one. Eventually, those bubbles merged. The universe became ionized again, but this time not because of heat, because of starlight. Scientists estimate that reionization was complete by about 1 billion years after the Big Bang. By then, the cosmic dark ages were over. The universe was luminous, filled with stars and galaxies, glowing with the light of creation. And it's been bright ever since. But here's a question that still puzzles astronomers. Where are those first stars now? We call them population 3 stars, a term that sounds oddly backwards but makes sense in context. Population 1 stars are the youngest, like our Sun, rich in heavy elements. Population 2 stars are older, with fewer heavy elements. And population 3 stars would be the very first. No heavy elements at all, just pure hydrogen and helium. But we've never seen one, not directly. If they existed, and the math says they must have, they burned out long ago. They were so massive that they lived fast and died young, exploding as supernovae or collapsing into black holes. None of them should still be shining today. But their remnants might still be out there. Black holes formed from the first stars. Neutron stars, incredibly dense and ancient. Or perhaps, in the most distant reaches of space, we might one day glimpse the faint light from a population 3 star that's been traveling toward us for over 13 billion years. In 2022, the James Webb Space Telescope began searching for signs of these ancient stars. By looking at the earliest galaxies, astronomers hope to find chemical signatures, patterns in the light that could only come from stars with no heavy elements. The search continues. The first stars are still hiding, somewhere in the deep history of the cosmos. But we're getting closer. Let's talk about what those first stars meant for the universe. Before them, the cosmos was simple. Hydrogen, helium, dark matter, and light. That's all. A universe with potential, but no complexity. After them, everything changed. The heavy elements forged in their cores and scattered by their explosions became the building blocks for the next generation of stars. And those stars, slightly richer in elements, created even more complexity. Over billions of years, the universe became chemically diverse. Carbon, nitrogen, oxygen, the elements essential for life, were rare at first. But with each generation of stars, they became more abundant. The universe was enriching itself, learning to create new forms of matter with every stellar death. It's a cycle. Stars are born from clouds of gas. They fuse lighter elements into heavier ones. They die, scattering those elements back into space. And from that enriched material, new stars form, continuing the process. Our Sun is a 3rd or 4th generation star. It formed from a cloud that had already been enriched by the deaths of earlier stars. That's why Earth has iron, silicon, oxygen, and all the other elements necessary for a rocky planet. Without the first stars, none of this would exist. Not planets, not water, not life. The universe would still be a cold, diffuse fog of hydrogen, drifting endlessly with no structure, no story, no future. The first stars gave the universe a past worth remembering and a future worth exploring. There's something almost heroic about those first stars, isn't there? They appeared in total darkness, born from nothing but gravity and time. They lived fast, burned bright, and died violently. But in their destruction, they made everything else possible. It's a pattern you see throughout the cosmos. Endings aren't just endings, they're beginnings. Death feeds life. Collapse creates opportunity. The universe doesn't waste anything. Even now, billions of years later, stars are still being born, still dying, still enriching the cosmos with new elements. The cycle hasn't stopped. If anything, it's become more intricate, more beautiful, more full of possibility. And you, yes, you, are part of that cycle. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of it was forged inside stars that lived and died long before the Earth even existed. You are not separate from the universe. You are continuous with it, made of the same materials, shaped by the same forces, part of the same unfolding story. Now, imagine what it must have been like when the first light appeared. For hundreds of millions of years, the universe had been waiting, dark, cold, silent. And then, somewhere in the vast emptiness, a single point of light flickered to life. Then, another, and another. Slowly at first, then faster, stars began to ignite across the cosmos, like fireflies appearing at dusk, one by one, until the darkness was no longer absolute. There was no one there to see it, of course. No eyes, no minds, no civilizations. Just the universe, waking up. Becoming aware of itself in the only way it knew how, through light. And in a sense, that process is still happening. Every time a new star is born, the universe becomes a little brighter. Every time a telescope captures the light from a distant galaxy, we're witnessing that ancient moment of awakening stretched across billions of years. The first stars may be gone, but their light is still traveling, still reaching us, still telling the story of how darkness became illumination. Let's sit with that for a moment. The idea that light from the first stars might still be out there, journeying through space, carrying information about the earliest moments of the universe's brightness. Some of that light has been traveling for so long that the stars that emitted it have long since died. But the light continues, persistent, patient, unaware that its source no longer exists. In a way, light is the universe's memory. It doesn't forget. It carries the past forward, inscribed in wavelengths and frequencies, waiting for someone or something to decode it. When astronomers study distant galaxies, they're not seeing them as they are now. They're seeing them as they were billions of years ago, when the light left them. The farther we look, the farther back in time we see. If we could somehow look far enough, we'd see the first stars, the first galaxies, the moment the cosmic dark ages ended and the universe began to glow. We're not there yet, but we're close. And every new telescope, every new observation, brings us one step closer to witnessing the birth of light itself. The first stars did more than illuminate the universe. They set the stage for everything that would come next. Galaxies clustering together, black holes growing at their centers, and eventually, solar systems forming with planets capable of supporting life. But galaxies themselves, they're stranger and more intricate than most people realize. Galaxies are not random. They don't scatter themselves across the universe by accident, drifting wherever chance takes them. They gather, they spiral, they collide and merge and dance around each other in patterns so intricate that scientists are still trying to understand the choreography. From a distance, a galaxy looks peaceful, a soft smudge of light, calm and eternal. But up close, it's chaos held together by gravity. Billions of stars, clouds of gas, stellar remnants, and at the center of almost every large galaxy, something that shouldn't exist, a supermassive black hole. These black holes aren't just passengers. They're not quiet bystanders. They shape the galaxies around them, feeding on matter, spewing out energy, sculpting the structure of entire star systems. And the strange part? We still don't fully understand how they got there, or why almost every galaxy has one, or what they're doing, hidden in the dark, pulling at the fabric of space-time. Galaxies are stranger than they first appear, and the more we look, the stranger they become. Let's start with something you've probably seen in photos: spiral galaxies. The Milky Way is one, so is Andromeda. They're beautiful, graceful arms of stars sweeping outward from a bright central bulge, like cosmic pinwheels frozen in slow rotation. But here's what's surprising. Those spiral arms aren't made of the same stars all the time. You might think that stars stay in the arms as the galaxy rotates, like paint on a spinning record. But that's not how it works. Stars move through the arms. The arms themselves are density waves, regions where stars and gas temporarily bunch together, like cars slowing down in a traffic jam. Imagine a highway during rush hour. The traffic jam doesn't move with the cars. It stays in one place while cars pass through it, slow down, then speed up again. Spiral arms work the same way. Stars drift in, linger for a while, then drift out. But the arm remains, always full of stars, always turning. It's one of those counterintuitive truths about the universe. What looks solid and permanent is actually fluid. What looks still is actually in motion. Galaxies breathe, shift, rearrange themselves on timescales so long we barely notice. Then there are elliptical galaxies. These don't have spiral arms. They're smooth, featureless blobs of stars, sometimes nearly spherical, sometimes stretched into elongated ovals. And unlike spirals, which are still forming new stars, elliptical galaxies are mostly quiet, old, settled. Scientists believe elliptical galaxies form through galactic collisions. When two spiral galaxies crash into each other, their structures are destroyed. Stars are flung into new orbits. Gas clouds collapse and ignite in a brief, intense burst of star formation. And when the chaos finally settles, what's left is an elliptical galaxy, a collection of old stars orbiting randomly with no organized structure. It sounds violent, and it is. But collision is a bit misleading. Galaxies are mostly empty space. When two galaxies merge, the stars themselves almost never hit each other. It's like throwing two swarms of bees together. The swarms intermingle, but the individual bees pass right by. Still, the gravitational disruption is immense. Stars are pulled into new trajectories. Entire regions of space are reshaped. And over millions of years, two galaxies become one. Our own Milky Way is on a collision course with Andromeda. In about 4.5 billion years, they'll merge. The night sky will change, new stars will form, and eventually, the two spiral galaxies will settle into a single elliptical galaxy, much larger and quieter than either one alone. But don't worry, the Sun and Earth, if it still exists, will likely survive, just in a different neighborhood. Now, let's talk about the centers of galaxies. At the heart of the Milky Way, about 26,000 light-years from Earth, there's a region called Sagittarius A space. You can't see it with ordinary telescopes. It doesn't emit visible light. But if you observe it with radio waves or X-rays, you'll find something extraordinary: a supermassive black hole, about 4 million times the mass of the Sun. It's not alone. Almost every large galaxy we've observed has a supermassive black hole at its center. Some are millions of times the Sun's mass, others are billions. The black hole at the center of the galaxy M87, for example, is about 6.5 billion solar masses, so large that its event horizon could swallow our entire solar system. And yet, for most of their existence, these black holes are quiet. They sit at the galactic center, spinning slowly, not doing much of anything. No light escapes, no sound. Just a silent gravitational anchor holding the galaxy together. But every now and then, something falls in. A star wanders too close, or a cloud of gas drifts toward the center. And when that happens, the black hole wakes up. Here's what it looks like when a supermassive black hole feeds. As matter spirals inward, it heats up. Friction and gravitational compression raise the temperature to millions of degrees. The material glows, first red, then white-hot, then blindingly bright in X-rays and ultraviolet light. This glowing disk of matter is called an accretion disk, and it can shine brighter than the entire galaxy. Some of the most luminous objects in the universe are not stars. They're supermassive black holes actively feeding. Astronomers call them quasars, short for quasi-stellar objects, because when they were first discovered, they looked like stars but were impossibly bright. It took decades to figure out what they were. Galaxies with black holes at their centers, so actively feeding that they outshine everything around them. The brightest quasar ever observed, called J05294351, is so luminous that it's estimated to be consuming the equivalent of one sun per day. Every single day, a star's worth of matter falls into its black hole, releasing energy in the process. And this has been going on for billions of years. Imagine that. A black hole so ravenous, so efficient, that it devours stars like we breathe air, constantly, effortlessly, without pause. But black holes don't just consume, they also give back. When matter spirals into a black hole, not all of it crosses the event horizon. Some of it gets caught up in powerful magnetic fields and is accelerated outward at nearly the speed of light, forming jets, narrow beams of energy and particles that shoot out from the black hole's poles. These jets can stretch for millions of light years. They plow through intergalactic space, carving out enormous bubbles, heating the surrounding gas, and sometimes triggering or suppressing star formation in distant regions. In a strange way, supermassive black holes regulate their own galaxies. If they feed too much, the energy they release can blow away the gas needed to form new stars, effectively starving the galaxy. If they're too quiet, the galaxy can produce stars unchecked, using up its gas reserves too quickly. It's a delicate balance, and somehow, over billions of years, galaxies and their black holes have learned to coexist, each shaping the other in an intricate cosmic feedback loop. Scientists still don't fully understand how this works. How does a black hole know when to feed and when to rest? How does a galaxy know how much gas to keep and how much to lose? The answers are still emerging, but one thing is clear. Black holes are not separate from galaxies. They're woven into the structure, essential to the story, as much a part of the galaxy as the stars themselves. Now here's the mystery that keeps astronomers awake at night. How did supermassive black holes form so quickly? When we look at the most distant galaxies that formed less than 1 billion years after the Big Bang, we find supermassive black holes already in place. Already billions of times the mass of the sun, already feeding, already bright. But how? Black holes grow by consuming matter or merging with other black holes. Both processes take time, and there shouldn't have been enough time in the early universe for black holes to grow that massive. Some scientists suggest that the first black holes formed directly from collapsing clouds of gas, bypassing the star stage entirely. These direct collapse black holes could have started much larger than stellar black holes, giving them a head start. Others propose that black holes in the early universe grew faster than expected, feeding on dense streams of gas that funneled directly into their centers. And there's another idea, more speculative but intriguing, that the seeds of supermassive black holes might have formed even earlier, perhaps in the first fraction of a second after the Big Bang. Tiny fluctuations in density could have created what are called primordial black holes, which then grew over time. The truth is, we don't know yet. It's one of the great unsolved puzzles of cosmology. The black holes are there, the evidence is undeniable, but their origin story remains incomplete. Let's step back and think about scale for a moment. The Milky Way contains about 200 to 400 billion stars. That's more stars than there are grains of sand on all the beaches on Earth. And yet, the Milky Way is just one galaxy among hundreds of billions, maybe trillions, in the observable universe. Each galaxy has its own structure, its own history, its own population of stars, planets, and black holes. Some are spiral, some elliptical, some irregular. Some are massive, some small. Some are actively forming stars. Others are quiet and old. And they're not evenly distributed. Galaxies cluster together, forming groups, clusters, and superclusters connected by filaments of dark matter. The universe has a structure, a vast web-like architecture that stretches across billions of light years. Our Milky Way is part of a small group called the Local Group, which includes Andromeda and about 50 smaller galaxies. The Local Group, in turn, is part of the Virgo supercluster, which contains thousands of galaxies. And the Virgo supercluster is just one small node in an even larger structure called the Laniakea supercluster, a region of space containing about 100,000 galaxies, all loosely connected by gravity, all drifting together through the expanding universe. We are so small, and yet we're mapping it, naming it, understanding it. A single species on a single planet in a single galaxy, somehow able to comprehend the structure of the cosmos itself. It's audacious, really, and beautiful. There's something humbling about galaxies, isn't there? They remind us that we're part of something unimaginably larger, that our sun is just one star among billions, that Earth is just one planet among countless others, that our entire existence is a brief flicker in the long, slow turning of the galaxy. And yet, here we are, looking up, measuring distances, decoding light, asking questions. We are the Milky Way becoming aware of itself, the universe observing its own structure. And in that act of observation, something shifts. The cosmos is no longer just objects and distances. It becomes story. It becomes meaning. You might wonder sometimes if any of this matters. If the universe is so vast and we're so small, does anything we do make a difference? But maybe the question is backwards. Maybe the vastness doesn't diminish us. It includes us. We're not separate from the galaxies, the black holes, the superclusters. We're continuous with them, made of the same atoms, shaped by the same forces, part of the same unfolding pattern. Galaxies don't exist to be admired. They don't spin for our benefit, but they exist. And so do we. And in the quiet act of noticing, of looking up and wondering, something beautiful happens. The universe recognizes itself. Galaxies are still forming, still colliding, still evolving. The cosmic story isn't finished. It's ongoing, dynamic, alive in its own slow, ancient way. And somewhere in all of that, somewhere in the spiral arms and the black holes and the clusters of light stretching across the dark, there are solar systems forming, planets cooling, conditions aligning in ways that might, just might, allow for something even stranger than galaxies to emerge: life. Planets should not exist. Think about it. A cloud of gas and dust drifting through space somehow decides to collapse. Gravity pulls it inward. It spins faster as it shrinks. And instead of just forming a single star and scattering the rest of the material into the void, it creates a family. Dozens, sometimes hundreds of orbiting worlds. Rocky planets close to the star. Gas giants farther out. Moons, rings, asteroids, comets. An entire solar system, structured and stable, persisting for billions of years. It's not random, it's not chaotic, it's organized, almost elegant. And yet, for most of history, we didn't know if planets even existed beyond our own solar system. We assumed they did. Statistically, it seemed likely. But we had no proof. Then, in 1992, astronomers detected the first confirmed exoplanets, not around a sun-like star, but around a pulsar, a rapidly spinning neutron star, the remnant of a supernova, planets that somehow survived the death of their star, or perhaps formed afterward from the debris. Since then, we've found thousands: rocky worlds, gas giants, ice giants, planets orbiting binary stars, planets closer to their suns than Mercury, planets so far out they take thousands of years to complete a single orbit. Every solar system is different, and yet they all started the same way, from nothing but dust. Let's go back to the beginning, to a cloud of gas and dust floating in space. This cloud is called a molecular cloud, and it's enormous. Some are hundreds of light years across, containing enough material to form thousands of stars. But it's also incredibly diffuse, thinner than the best vacuum we can create in a laboratory. For millions of years, it just drifts. Cold, dark. Mostly hydrogen, with traces of helium and heavier elements, carbon, oxygen, silicon, iron, leftovers from earlier generations of stars that lived and died. Then something disturbs it. Maybe a nearby supernova sends a shock wave rippling through space. Maybe two molecular clouds collide. Maybe a passing star's gravity tugs on it just enough. Whatever the cause, a region of the cloud begins to collapse. Gravity takes over. Atoms pull toward each other. The cloud fragments into smaller clumps, each one collapsing on its own. And at the center of one of those clumps, a star begins to form. But not all the material falls into the star. Some of it remains in orbit, spinning around the newborn sun, forming a flat disk, what astronomers call a protoplanetary disk. This disk is where planets are born. At first, the disk is just gas and dust, tiny particles, grains of silicate, ice crystals, carbon molecules, floating in a thin haze, orbiting the young star. But over time, something remarkable happens. The particles begin to stick together. It starts small. Two dust grains collide gently and cling to each other through static electricity or van der Waals forces, the same forces that let a gecko walk on a ceiling. Then another grain sticks, and another. Slowly, over thousands of years, these grains grow into pebbles, pebbles into rocks, rocks into boulders, boulders into planetesimals, objects a few kilometers across, large enough that their own gravity starts to matter. And once gravity takes over, growth accelerates. Planetesimals collide and merge. The largest ones grow faster, sweeping up everything in their orbital paths. Within a few million years, the disk is no longer a smooth haze. It's filled with hundreds of planet-sized bodies, jostling for position, colliding, merging, fragmenting. It's violent, chaotic. But slowly, order emerges. The largest bodies survive. The smaller ones are absorbed or ejected. And what's left is a solar system, a handful of planets in stable orbits, separated by vast expanses of emptiness. Our solar system formed this way, about 4.6 billion years ago. And it's still settling. Even now, asteroids drift, comets fall toward the sun, moons shift in their orbits. The process never fully stops. It just slows down. Here's something most people don't realize. Planets migrate. When a planet forms, it doesn't necessarily stay where it started. Gravitational interactions with the gas in the protoplanetary disk can cause it to drift inward or outward, sometimes by enormous distances. In our solar system, scientists believe Jupiter formed much farther from the Sun than it is now, then migrated inward before drifting back out. This migration had massive consequences. It scattered asteroids, destabilized orbits, and may have prevented a large planet from forming where the asteroid belt is today. Some exoplanets show even more extreme migration. We've discovered hot Jupiters, gas giants that orbit their stars closer than Mercury orbits the Sun. They couldn't have formed there. It's too hot, too close to the star for gas to condense. They must have formed farther out, then spiraled inward, perhaps pushed by interactions with other planets or the disk itself. In many cases, these migrating planets likely destroyed smaller rocky worlds that were in their way. Entire solar systems rearranged, planets flung into their stars or ejected into interstellar space. Our solar system is relatively calm by comparison, but it wasn't always. Early in its history, the planets shifted, collided, and settled into their current orbits. Earth itself may have formed closer to where Mars is now, then drifted inward. The solar system you see today is not the solar system that first formed. It's the survivor of billions of years of gravitational chaos. Let's talk about Earth's formation. About 4.5 billion years ago, a rocky planetesimal, maybe the size of Mars, collided with the young Earth in a glancing blow. The impact was so violent that it vaporized the surface of both bodies. Molten rock sprayed into space. Some of it fell back to Earth. Some of it coalesced in orbit, forming a ring of debris that eventually collapsed into a single large body: the Moon. This event, called the Giant Impact Hypothesis, explains several mysteries. Why the Moon's composition is so similar to Earth's. Why it's so large relative to Earth. No other planet in the solar system has a moon so proportionally big. Why Earth's rotation is tilted at 23.5 degrees, giving us seasons. Without that collision, Earth might be a very different place. No moon to stabilize the tilt of our axis. No tides to stir the oceans. Perhaps no life, or at least not the kind we recognize. The Moon is not just Earth's companion. It's Earth's sibling, born from the same catastrophic moment. And every night, when you look up and see it glowing softly in the sky, you're seeing a piece of your own planet, suspended in orbit, held there by gravity and history. Here's another surprising fact. Most of the water on Earth didn't start here. When Earth first formed, it was hot. So hot that any water would have boiled off into space. The early Earth was a molten hellscape, bombarded by asteroids, its surface glowing red under a sky thick with vaporized rock. So, where did the oceans come from? The leading theory is that water was delivered later, during a period called the Late Heavy Bombardment, about 4.1 to 3.8 billion years ago, when the inner solar system was pummeled by asteroids and comets. Comets, in particular, are icy bodies from the outer solar system. When they crashed into Earth, they brought water, lots of it. Over millions of years, enough water accumulated to fill the oceans. Some scientists also believe that asteroids contributed. Certain types of asteroids, called carbonaceous chondrites, contain hydrated minerals, water locked inside rocks. When these asteroids hit Earth, the water was released. So, the water you drink, the water in the oceans, the water in your cells, it's ancient. It's older than life. It came from space, delivered by impacts, and has been cycling through Earth's systems for billions of years. You are made of stardust, and you're also made of comet water. Not all planets are lucky enough to end up in what astronomers call the habitable zone. This is the region around a star where conditions are just right for liquid water to exist on a planet's surface. Too close to the star, and water boils away. Too far, and it freezes. Earth sits comfortably in the middle of the sun's habitable zone. But it's not just about distance. It's also about atmosphere, size, magnetic fields, and a dozen other factors. Venus, for example, is only slightly closer to the sun than Earth, but its thick atmosphere traps heat so efficiently that surface temperatures reach 900 degrees Fahrenheit, hot enough to melt lead. Any water it once had evaporated long ago. Mars, on the other hand, is too far and too small. It lost most of its atmosphere early in its history, and what little water remains is frozen in the polar ice caps or locked underground. Earth got lucky, just the right size, just the right distance, just the right atmosphere, a magnetic field strong enough to protect against solar wind, a moon to stabilize its tilt, and water, lots of water, delivered at just the right time. It's not a miracle exactly, but it's rare, very rare. Out of the thousands of exoplanets we've discovered, only a handful might be in the habitable zone of their stars. And of those, even fewer probably have the right conditions for life. We're beginning to realize that Earth-like planets might be uncommon, not impossible, just uncommon. Now, here's a thought that might change the way you see the night sky. Every star you see up there, every single one, could have planets. Statistically, most of them probably do. In 2013, astronomers analyzing data from the Kepler Space Telescope estimated that there are at least 100 billion planets in the Milky Way alone. And that's a conservative estimate. Some are gas giants, inhospitable and stormy. Others are rocky, but too hot or too cold for life. But some, maybe a few billion, might be in the habitable zone, might have liquid water, might, just might, host life. We haven't found definitive evidence of life beyond Earth yet, but we're looking. Telescopes are scanning the atmospheres of distant planets, searching for biosignatures, chemical markers like oxygen or methane that could indicate the presence of living organisms. The James Webb Space Telescope is already analyzing exoplanet atmospheres in unprecedented detail. In the coming decades, new missions will push further, looking at smaller, more Earth-like worlds. If life exists elsewhere, and many scientists believe it does, we might be the generation that finds it, or perhaps we might discover that we're alone. That Earth is the only world in the Milky Way, maybe even the universe, where life took hold. Both possibilities are staggering, and we're on the edge of finding out which one is true. Let's sit with that for a moment. The universe is so vast, so old, so full of planets, and yet, as far as we know, Earth is the only place where life exists. It's tempting to assume that life must be common, that with so many stars, so many planets, the odds are in favor of life emerging somewhere else. But consider this. Life on Earth required not just the right planet, but the right sequence of events, the right chemistry, the right environmental conditions, billions of years of stability, random mutations guided by natural selection, an atmosphere that could support complex organisms. And even on Earth, life took a long time to get started. The planet formed 4.5 billion years ago. The first simple life appeared about 3.8 billion years ago. But complex life, multicellular organisms, animals, plants, didn't appear until about 600 million years ago. For most of Earth's history, life was just bacteria and algae. Invisible, simple, struggling to survive. Maybe life is common, but intelligence is rare. Maybe planets like Earth are common, but planets with breathable air and stable climates are rare. Maybe we're not alone, but we're isolated, separated by such vast distances that we'll never meet. Or maybe we're unique, the one place in the universe where atoms organize themselves into something that could look back at the stars and wonder. Either way, it's a gift. To be here, to be alive, to exist on a planet that somehow, against all odds, became home. Planets are still forming. Right now, in distant molecular clouds, dust is clumping together, stars are igniting, protoplanetary disks are spinning into new worlds. The process that created Earth is still happening, over and over, across the galaxy. New solar systems are being born, new planets are cooling, new chances for life are emerging. And on some of those worlds, billions of years from now, Beings might look up at their own night sky and wonder the same things we wonder. Where did we come from? Are we alone? What lies beyond the stars? The universe is not finished. It's still creating, still experimenting, still becoming. And in the quiet spaces between stars, in the places where dust begins to gather and gravity begins to pull, the next chapter is already being written. There was a moment when the universe held its breath, when planets had formed, oceans had cooled, and the stage was set. But nothing moved, no cells divided, no metabolism hummed, just chemistry, complex, restless chemistry, waiting at the edge of something new. And then, somewhere on the young Earth, in a tide pool or a deep sea vent or a warm volcanic spring, molecules arrange themselves in just the right way. Not by design, not with intention. Just by chance, by trial and error, repeated trillions of times across millions of years. And life began. Not with a bang, not with purpose, just with replication. A molecule that could copy itself. And once copying started, everything changed. Evolution began, complexity accumulated, and over billions of years, single cells became forests, oceans, mines. Became you. The origin of life is still one of science's greatest mysteries. But the more we learn, the more it seems like life wasn't a miracle. It was inevitable. A natural consequence of chemistry, given enough time and the right conditions. And if that's true, then we might not be alone after all. Let's start with the basics. What is life? It sounds like a simple question, but scientists still debate the answer. Is a virus alive? It can't reproduce on its own. Is a flame alive? It consumes fuel, grows, and spreads. What about a self-replicating computer program? Most biologists agree on a few essential criteria. Life must be able to reproduce. It must metabolize, take in energy and use it. It must respond to its environment. And it must evolve, change over generations in response to selection pressures. By those standards, the first life on Earth was incredibly simple, probably just a molecule, or a cluster of molecules, that could make copies of itself using raw materials from the environment. No cells yet, no DNA, no membranes separating inside from outside, just chemistry that had learned by accident to persist. Scientists call this the transition from chemistry to biology. And it's one of the hardest things to study because it happened so long ago that almost no evidence remains. But we're getting closer, and the clues are surprising. One of the most famous experiments in the study of life's origins happened in 1952. A graduate student named Stanley Miller, working with his advisor Harold Urey, wanted to test whether the building blocks of life could form naturally on the early Earth. They built a simple apparatus, a sealed glass container filled with water, methane, ammonia, and hydrogen, gases they believe were present in Earth's early atmosphere. They added heat to simulate volcanic activity and electric sparks to simulate lightning. Then they waited. After just 1 week, the water in the flask had turned murky. When Miller analyzed it, he found amino acids, the building blocks of proteins, complex organic molecules formed from nothing but simple gases and energy. It was astonishing. The experiment showed that the chemistry of life wasn't special or rare. It could happen spontaneously, given the right conditions. Since then, similar experiments have produced even more complex molecules, sugars, nucleotides, lipids, all the fundamental components of living cells arising naturally from non-living chemistry. Life, it seems, wants to happen, or at least, the chemistry that leads to life is eager, persistent, always teetering on the edge of organization. But there's a problem, a big one. Building blocks are one thing, but life requires more than just amino acids and sugars floating in water. It requires organization. It requires information. Modern life stores information in DNA, a long, elegant molecule shaped like a twisted ladder. Each rung of the ladder is made of one of 4 chemical bases: adenine, thymine, cytosine, and guanine. The sequence of the bases encodes instructions for building proteins, which do the actual work of keeping a cell alive. But DNA can't replicate itself without proteins, and proteins can't be made without DNA. It's a chicken and egg problem. Which came first? For decades, this puzzle stumped scientists until they realized they were asking the wrong question. In the 1980s, researchers discovered that RNA, a molecule similar to DNA but simpler, can do both jobs. It can store information like DNA, and it can act as a catalyst like a protein. This led to what's called the RNA world hypothesis, the idea that early life was based on RNA, not DNA. RNA molecules that could replicate themselves, catalyze reactions, and evolve. Only later did DNA and proteins take over, because they're more efficient and stable. It's still a hypothesis. We don't have proof, but it fits the evidence we do have, and it solves the chicken and egg problem elegantly. Life might have started with a single self-replicating RNA molecule, floating in a primordial soup, copying itself over and over, making mistakes that sometimes made it better at copying. And from that humble beginning, everything else followed. Now, where did this happen? Where on Earth did life first appear? For a long time, scientists assumed it was in a warm little pond, as Charles Darwin once put it, a shallow body of water where sunlight, minerals, and organic molecules could mix and react. But in the 1970s, oceanographers discovered something unexpected: hydrothermal vents on the ocean floor. These vents are cracks in the Earth's crust where superheated water, rich in minerals like iron, sulfur, and hydrogen, pours out into the cold, dark ocean. Around these vents, entire ecosystems thrive, powered not by sunlight, but by chemical energy. Some scientists now believe that life might have started at these vents. The conditions are ideal: a constant supply of energy, a steady flow of raw materials, and natural mineral surfaces that could have acted as catalysts, helping molecules assemble and react. One type of vent, called alkaline hydrothermal vents, is especially intriguing. These vents produce warm, mineral-rich water that's not too hot, around 40 to 90 degrees Celsius, and they create natural pH gradients, which some researchers believe could have powered early metabolism, long before cells had developed their own energy systems. In 2019, a team of scientists recreated the conditions of these vents in a laboratory. They found that simple organic molecules could spontaneously form cell-like structures, complete with membranes and the beginnings of metabolism. Life might not have begun in a sunlit pond. It might have begun in the deep, dark ocean, where heat and chemistry met in just the right way. But here's the most humbling part: we don't know when life began. The Earth formed about 4.5 billion years ago. For the first few 100 million years, it was uninhabitable, molten, bombarded by asteroids, its surface covered in oceans of magma. But by about 4 billion years ago, the planet had cooled. Oceans had formed. The late heavy bombardment was ending. And soon after, maybe as early as 3.8 billion years ago, life appeared. How do we know? Tiny fossils mostly. Fossilized bacteria preserved in ancient rocks. Chemical signatures and minerals that suggest biological activity. Stromatolites, layered structures built by colonies of microbes, some of which are 3.5 billion years old. Life appeared quickly. Almost as soon as Earth became habitable, life took hold. That suggests something profound: that life isn't a fluke, that given the right conditions, it emerges naturally, almost inevitably. Or maybe we're just incredibly lucky. Maybe life is rare, and Earth happened to win the cosmic lottery in its first few 100 million years. We won't know until we find life elsewhere, or fail to find it, despite looking everywhere. For most of Earth's history, life was simple. Just bacteria and archaea, single-celled organisms, invisible to the naked eye, drifting in the oceans, coating rocks, living in the soil. For 2 billion years, that's all there was. No plants, no animals, no eyes to see, no ears to hear. Just microbes, endlessly dividing, evolving, spreading across every environment they could tolerate. It sounds boring, but it wasn't. Those microbes were doing something extraordinary. They were changing the planet. About 2.4 billion years ago, a group of bacteria called cyanobacteria evolved the ability to perform photosynthesis. They use sunlight to split water molecules, releasing oxygen as a waste product. At first, the oxygen didn't accumulate. It reacted with iron in the oceans, forming rust that settled to the ocean floor. You can still see this rust today. It's what gives ancient rock formations their distinctive red bands. But eventually, all the iron was used up, and the oxygen began to accumulate in the atmosphere. This was catastrophic for most life at the time. Oxygen is reactive, corrosive. For organisms that had evolved in an oxygen-free world, it was poison. Many species went extinct, but a few adapted. And those that did gained access to a powerful new source of energy. Oxygen-based respiration is far more efficient than the metabolic pathways used by earlier life. It allowed organisms to grow larger, more complex, more active. The Great Oxidation Event, as it's called, was Earth's first major environmental crisis, but it was also the foundation for everything that came after. Without oxygen, there would be no animals, no plants, no fungi, no you. Life didn't just adapt to the planet. Life created the planet as we know it. Now, here's a question that haunts astrobiology. Is life inevitable, or was it a one-time accident? If you could rewind Earth's history and let it play out again, would life emerge a second time? Or was it a series of improbable coincidences, so unlikely that it might never happen again anywhere in the universe? We don't know. We only have one example: Earth. And you can't draw conclusions from a sample size of one. But the speed with which life appeared on Earth suggests that it might be common. The building blocks of life form easily. The chemistry is robust, and the universe is full of planets. Some scientists estimate that there could be billions of habitable planets in the Milky Way alone. If even a small fraction of those planets develop life, the galaxy could be teeming with microbes. But intelligence? That's a different question. Life might be common, but intelligent life that builds tools, asks questions, explores space, might be extraordinarily rare. Consider this. Life appeared on Earth 3.8 billion years ago. But humans, modern humans with language and art and science, only appeared about 300,000 years ago. For 99.99% of life's history on Earth, there was no intelligence, no technology, no civilization. Intelligence might be a fluke, a side effect of evolution that happened once, by accident, and might never happen again. Or maybe intelligence is inevitable too, given enough time. Maybe on other worlds, other minds are waking up, looking at their own skies, asking the same questions we ask. We're searching, listening, hoping to find a signal, a sign that we're not alone. And maybe one day we will. Let's think about what life means, not just biologically, but philosophically. For billions of years, the universe was just physics. Particles moving according to rules, stars forming, planets cooling, molecules reacting. No purpose, no meaning, just process. And then life appeared, and suddenly there was something new: intentionality, self-preservation, desire, reproduction. Life is matter that cares about itself. Matter that tries to persist, to spread, to continue. And eventually, in at least one small corner of the universe, life became complex enough to reflect on its own existence, to ask why, to create art, music, stories, to build telescopes and peer into the past, trying to understand how it all began. You are the universe becoming conscious of itself. Atoms, arranged in such a way that they can wonder where they came from. That's not just biology, that's something almost miraculous. Not in a supernatural sense, but in the sense of being profoundly unlikely and profoundly beautiful. Life is fragile, a thin film of biology clinging to the surface of a single planet, dependent on sunlight, water, oxygen, and 1,000 other delicate conditions. But it's also resilient. Life has survived ice ages, asteroid impacts, volcanic eruptions, mass extinctions. It's adapted to deserts, deep oceans, acidic hot springs, frozen tundra. Wherever there's energy and liquid water, life finds a way. And now, life is beginning to leave its planet. Humans have walked on the moon. Rovers have explored Mars. Spacecraft have visited the outer planets and are now drifting into interstellar space. It's a small step, a tentative gesture, but it's a step nonetheless. Life, which began in a tide pool or a deep sea vent, is reaching outward, learning to leave home. And maybe one day it will spread to other worlds, other star systems, other galaxies. Or maybe we'll find that life is already out there, waiting, that we're not the first or the only or even the most interesting. Either way, the story of life is far from over. It's still being written, still unfolding, still full of surprises. We've traveled so far now, from the moment before the Big Bang to the birth of stars, the formation of galaxies, the creation of planets, and the emergence of life. But there's one more layer to this story, one more mystery that ties it all together. Because the universe isn't just a collection of objects, it's also a collection of moments, stretched across time, woven into something we're only beginning to understand. And that brings us to the strangest question of all. Time is not what you think it is. We experience it as a river, flowing in one direction, from past to future, always forward, never back. Seconds tick by, minutes accumulate, years pass. And we ride along, carried by a current we can't see or stop. But according to physics, time doesn't flow. It just is. Past, present, and future all exist simultaneously, laid out like pages in a book. We only perceive one moment at a time, but the entire timeline, every moment that has ever happened or will ever happen, exists all at once. Einstein called this the block universe. And if he's right, then the Big Bang isn't in the past. It's still there, frozen in time, just as real as this moment you're experiencing now. Time is the strangest dimension, the most familiar and the most mysterious. And the deeper we look, the less we understand. Let's start with something simple, the speed of light. In everyday life, light seems instantaneous. You flip a switch and the room lights up. You look at the stars and they shine. No delay, no waiting. But light does have a speed, 209,792 kilometers per second. Fast, unimaginably fast, but not infinite. And because light has a speed, there's a delay between when something happens and when we see it. When you look at the sun, you're not seeing it as it is now. You're seeing it as it was 8 minutes ago, the time it takes for light to travel from the sun to Earth. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd still see it shining, still feel its warmth, until the last light reached us. The farther you look, the farther back in time you see. The nearest star, Proxima Centauri, is 4.24 light-years away. When you see it, you're seeing light that left the star over 4 years ago, If someone on a planet orbiting Proxima Centauri is looking at Earth right now, they're seeing Earth as it was 4 years in the past. We don't just look across space when we use telescopes, we look across time. And the most distant objects we can see, galaxies near the edge of the observable universe, are showing us light that's been traveling for over 13 billion years. We're seeing them as they were when the universe was young, not long after the first stars formed. Light is a time machine. Every photon carries a message from the past, traveling through the void, waiting for someone to receive it. Here's where it gets stranger. According to Einstein's theory of relativity, time isn't the same everywhere. It flows at different rates depending on how fast you're moving and how strong the gravitational field is around you. This isn't science fiction. It's been measured, tested, confirmed over and over again. In 1971, scientists placed atomic clocks on airplanes and flew them around the world. When they landed and compared those clocks to identical clocks that had stayed on the ground, they found a difference. The clocks on the planes had ticked slightly slower. Just a few nanoseconds, but measurable. Why? Because the planes were moving faster than the clocks on the ground. And according to relativity, the faster you move through space, the slower you move through time. This effect is called time dilation. And it's not just theoretical, it's real. GPS satellites orbiting Earth have to account for time dilation, or they'd give you the wrong location. Time moves slightly faster in orbit than it does on the surface of the Earth, because the satellites are farther from Earth's gravitational field. If you spent a year on the International Space Station, you'd age slightly less than someone who stayed on Earth, about 0.007 seconds less. Not much, but real. Time is flexible. It bends, it stretches, it slows down near massive objects and speeds up in empty space. You and I are not experiencing the same now. We're close enough that the difference is unnoticeable, but someone on a spaceship traveling near the speed of light would experience time very differently than we do. For them, hours might pass. For us, years. Now, let's talk about something even stranger. The twin paradox. Imagine two twins. One stays on Earth. The other boards a spaceship that travels at nearly the speed of light to a distant star and back. From the perspective of the twin on the spaceship, the journey takes a few years. But when they return to Earth, they find that decades have passed. Their twin, who stayed behind, has aged much more. This isn't a thought experiment. It's a prediction of relativity, and it's been confirmed experimentally using particles that decay over time. When those particles are accelerated to high speeds, they live longer, from our perspective, because time is moving slower for them. The twin who traveled through space hasn't just moved through space. They've moved through time differently than their sibling. Time isn't universal. There's no single now that everyone experiences. Your now is different from someone else's, depending on where you are and how fast you're moving. It's disorienting, isn't it? To realize that time, something that feels so absolute, so constant, is actually relative, mutable, personal. But here's the question that haunts physicists. Does time even exist? Some scientists believe that time is an illusion, that what we call time is just a way our brains organize cause and effect. That fundamentally, the universe doesn't have a past or a future, only states of existence layered across what we perceive as a timeline. Think of it this way. If you could see the entire universe from outside, if you were somehow beyond space and time, looking at everything at once, you wouldn't see things happening. You'd see the whole history of the universe laid out like a sculpture. Every moment, from the Big Bang to the far future, existing simultaneously. This is the block universe model, and it suggests that the flow of time, the sense that the present is moving forward, is something that only happens in our minds. a side effect of consciousness, not a fundamental feature of reality. If that's true, then the past isn't gone. It's still there, frozen, just as real as this moment. And the future isn't waiting to happen. It's already happened. We just haven't experienced it yet. It's a strange, unsettling idea, but it fits the equations of relativity perfectly. And some physicists take it very seriously. Let's sit with that for a moment. If the block universe is real, then everything that has ever happened and everything that will ever happen is already determined. The past, present, and future all coexist, unchanging, eternal. You might wonder, does that mean we don't have free will? If the future already exists, are our choices already made? Philosophers and physicists have debated this for centuries. Some argue that the block universe is compatible with free will, that even if the future exists, we still experience making choices, and those choices are still ours. Others argue that it's incompatible, that if the future is fixed, our sense of agency is an illusion. There's no consensus, just questions layered on questions. But here's something worth considering. Even if the future is determined, you don't know what it is. You still have to live through it, make decisions, experience uncertainty. The subjective experience of time, the feeling that the present is real and the future is unknown, remains whether or not time truly flows. Maybe that's enough. Maybe the illusion is all we need. Now, let's talk about entropy. This is one of the few places where time does seem to have a direction, a distinction between past and future that can't be reversed. Entropy is a measure of disorder. In simple terms, it's the tendency of systems to move from order to chaos. A cup of hot coffee cools down, mixing its heat with the surrounding air. A sandcastle crumbles, a star burns out. The second law of thermodynamics says that entropy always increases over time. Things fall apart, energy spreads out, order becomes disorder. And this gives time an arrow. You can tell the difference between a video playing forward and a video playing backward because some processes only happen in one direction. Eggs break, but they don't spontaneously reassemble. Ice melts, but puddles don't freeze on their own in a warm room. Why? Because there are far more ways for things to be disordered than ordered. Randomness favors chaos. But here's the mystery. The laws of physics are time symmetric. If you reverse the direction of time in an equation, the math still works. A ball thrown upward could just as easily be a ball falling downward, played in reverse. So, where does the arrow of time come from? Why does entropy increase? Why does time seem to flow forward? The best answer we have is that the universe started in a highly ordered state, the Big Bang, and has been moving toward disorder ever since. Entropy increases because the universe began with low entropy, and it's been spreading out, cooling down, moving toward equilibrium ever since. Time's arrow isn't a law of physics. It's a consequence of initial conditions. The Big Bang set the clock ticking, and we're riding the wave of increasing entropy from then until now. Here's another thought that might unsettle you. The present doesn't last. By the time you finish reading this sentence, the moment you started it is already in the past. The present is always slipping away, vanishing into memory the instant it arrives. Neuroscientists estimate that what we experience as now is actually a window of about 2 to 3 seconds. Your brain takes sensory information from the recent past, integrates it, and presents it to your consciousness as the present moment. But really, you're always living slightly in the past. By the time your brain processes what you see and hear, the moment has already passed. The present is an illusion, constructed by your brain to give you a coherent sense of continuity, a way of stitching together the flow of experience into something that feels like a single, continuous now. But the now you experience isn't the same as someone else's now, and it's not even perfectly aligned with your own body. Your brain is constantly adjusting, compensating for delays, creating a seamless experience of time, even though the underlying reality is fragmented. We don't experience time directly. We experience a story our brain tells us about time. And that story is powerful, convincing, essential. But it's still just a story. Let's come back to the beginning, to the Big Bang, to the moment time started. If time is a dimension, like space, then the Big Bang wasn't just the beginning of space. It was the beginning of time itself. Before the Big Bang, there was no before. The question, what happened before time, doesn't make sense because before requires time, and time didn't exist yet. This is one of the hardest concepts to grasp. We're so used to thinking of time as infinite, as always existing, that the idea of time having a starting point feels impossible. But according to relativity, time and space are intertwined. They are part of the same fabric, space-time, and the Big Bang was the moment when space-time itself began. You can't stand outside space-time and watch it begin because there's no outside. Everything that exists, every location, every moment is inside space-time. The Big Bang is the boundary, the edge, the point before which nothing can be said. It's not that there was a void before the Big Bang. It's that before doesn't apply. Time itself is part of what was created. So where does that leave us? Time is strange, flexible, possibly illusory, possibly eternal, possibly just a dimension like any other, stretched out across the universe, waiting to be understood. We don't have all the answers. We might never have all the answers. But we're asking the right questions. And slowly, carefully, we're uncovering the structure of reality beneath the surface of experience. Time might not flow. The present might not be real. The future might already exist. But here you are, experiencing this moment, wondering about the next. And maybe that's the real mystery. Not what time is, but why it feels the way it does. Why we care about it. Why we measure it, chase it, mourn its passing. Time gives meaning to existence. Without it, there would be no change, no growth, no stories. Everything would exist in a frozen, eternal now, with no beginning and no end. Time is what allows the universe to unfold, to become, to surprise itself. And in that unfolding, something beautiful happens. Not just the birth of stars and planets, but the emergence of beings who can look back at it all and ask quietly, how did this happen? Why does anything exist at all? Which brings us to the final question, the one that ties everything together. Why is there something instead of nothing? It's the oldest question, the deepest question, the one that every civilization, every philosophy, every religion has tried to answer in its own way. Science has taken us far. We've traced the universe back to the Big Bang, back to the first fraction of a second, back to a moment so small and so hot that the laws of physics as we know them break down. But we can't go back any further. We can't see past that barrier. And so the question remains, hanging in the silence, why does anything exist at all? Some scientists believe the answer might lie in quantum mechanics, that the universe didn't need a cause. It simply emerged from the quantum foam, a random fluctuation that happened to persist. That existence itself is a kind of accident, beautiful and improbable, but not requiring explanation beyond the strange rules of quantum probability. Others think the answer is deeper, that there might be a reason, a principle we haven't discovered yet, that explains why reality prefers being to non-being. We don't know, and maybe we never will. But the question itself is worth asking, because in asking, we're doing something extraordinary. We're participating in the universe's attempt to understand itself. Let's take a step back, a long step, and look at the whole story. 13.8 billion years ago, the universe began. Not in a place, but as a place. not at a time, but as time. Everything that would ever exist, every star, every planet, every atom, every thought, was compressed into something unimaginably small, and then it expanded, rapidly, violently, silently. In the first second, the forces of nature separated. Quarks formed, then protons and neutrons. Within minutes, the first atomic nuclei appeared, hydrogen and helium, the raw materials for everything that would follow. For hundreds of millions of years, the universe was dark, just gas, drifting in the cold, waiting for gravity to gather it into stars. And then the first stars ignited. Massive, short-lived, brilliant. They burned fast and died violently, scattering heavy elements into space: carbon, oxygen, iron, the building blocks of planets, the building blocks of life. Galaxies formed, structured by dark matter we still don't fully understand. Black holes grew at their centers, shaping and regulating star formation across billions of years. Planets coalesced from dust. Some were hot, some cold. Some had water. And on at least one planet, maybe more, conditions aligned in just the right way for chemistry to become biology. Life appeared, simple at first, just molecules that could copy themselves. But over billions of years, those molecules became cells. Cells became organisms. Organisms became ecosystems. And eventually, one lineage of life developed something unprecedented: consciousness, the ability to reflect, to wonder, to ask why. And here we are. You are made of atoms forged in the cores of dying stars. You are made of water delivered by comets. You are made of carbon and oxygen and nitrogen, elements that didn't exist until stars created them. You are not separate from the universe. You are continuous with it, made of the same materials, shaped by the same forces, part of the same story. And that story is still unfolding. The universe is still expanding. Stars are still being born. Galaxies are still colliding. Planets are still forming. And on some of those planets, life might be beginning right now. Molecules learning to replicate, chemistry learning to persist. The story isn't over. It's ongoing, and you're part of it. Every breath you take is made of atoms that were once inside stars. Every thought you think is a pattern of electrical signals shaped by billions of years of evolution. Every question you ask is the universe trying to understand itself. You are the cosmos looking back at its own history, trying to remember, trying to understand. There's something humbling about that, isn't there? We're so small, a single species on a single planet, orbiting a single star, in one galaxy among hundreds of billions. And yet, we're also extraordinary. We've figured out how the universe began. We've measured the age of stars. We've discovered planets around other suns. We've decoded the chemistry of life. We've peered back to the earliest moments of time and seen the faint glow of creation itself. We've done this with nothing but curiosity and patience, with telescopes and equations, with experiments and observations. We've done this even though the universe doesn't make it easy. Even though most of reality is invisible, dark matter, dark energy, dimensions we can't perceive. Even though the answers we find often lead to deeper questions, we keep looking, keep wondering, keep asking why. And maybe that's the point. Maybe the universe isn't meant to be fully understood. Maybe it's meant to be endlessly explored, endlessly surprising, endlessly beautiful. Let's think about the future for a moment. The universe is 13.8 billion years old. That sounds ancient. But compared to how long it will last, it's young. Very young. Stars will keep shining for trillions of years. The sun has about 5 billion years left before it swells into a red giant and engulfs the inner planets. But other stars, smaller, cooler red dwarfs, will burn for 10 trillion years or more. Eventually, though, all the stars will die, all the gas will be used up. The universe will grow cold and dark, filled with black holes and the faint remnants of dead stars. Trillions and trillions of years from now, even the black holes will evaporate, radiating away their mass as Hawking radiation. And what will be left is a thin, cold soup of particles, spread so far apart that they'll never interact again. Scientists call this the heat death of the universe. Not a dramatic end, but a quiet fade. A universe that has run out of energy, settled into perfect equilibrium, incapable of change. It sounds bleak, but it's also so far in the future that it's almost meaningless. Right now, the universe is young, vibrant, full of stars and galaxies and possibilities. And right now, life exists, consciousness exists, meaning exists. That's not nothing, that's everything. Here's something worth holding on to. The universe didn't have to be this way. The laws of physics could have been different. The constants that govern gravity, electromagnetism, and nuclear forces could have had different values. If gravity were slightly stronger, stars would burn out too quickly for life to develop. If it were slightly weaker, stars wouldn't form at all. If the strong nuclear force were just a little different, atoms wouldn't hold together. If the weak nuclear force were different, stars wouldn't produce the elements necessary for life. The universe is finely tuned, not perfectly. There's plenty of chaos, plenty of waste, plenty of emptiness. But the fundamental rules are balanced in a way that allows for complexity, for structure, for stars and planets and life. Some scientists see this as evidence of a multiverse, billions of universes, each with different laws of physics. And we just happen to live in one where the conditions are right. Others see it as profound mystery, one that hints at something deeper we don't yet understand. Either way, it's astonishing. The universe is not only real, it's capable of supporting life, of supporting minds that can ask questions, of supporting beings who can look up at the stars and feel wonder. You might be wondering, does any of this matter? Does it matter that the universe is 13.8 billion years old? That stars are made of plasma? That black holes exist at the centers of galaxies? That time might not flow the way we think it does? On one level, no. These facts don't change your daily life. They don't pay the bills or solve immediate problems. But on another level, yes. Deeply, profoundly, yes. Because understanding where you come from changes how you see yourself. Knowing that you're made of stardust doesn't just add a poetic flourish to your existence. It connects you to something vast, ancient, and ongoing. You're not an accident. You're not separate from the cosmos. You're a natural consequence of 13.8 billion years of cosmic evolution. You are the universe, waking up and noticing itself. And that awareness, that sense of connection, can change everything. It can make you feel smaller and larger at the same time, humbler and more significant, part of something so big that it defies comprehension, and yet intimately personally involved in its unfolding story. So, where does that leave us? We started with nothing, with a question mark, a moment before moments, a place before places. And now, here we are, billions of years later, sitting on a small planet, looking up at the stars, trying to piece together the story of how it all began. We've learned so much, but there's so much more we don't know. We don't know what dark matter is. We don't know why the universe is expanding faster and faster. We don't know how life began, or if it exists elsewhere. We don't know what came before the Big Bang, or if that question even makes sense. But we're looking, we're asking, we're building telescopes and launching spacecraft and running experiments. We're mapping the cosmos, one photon at a time, and maybe one day we'll find the answers, or maybe we'll find new questions, even deeper and stranger than the ones we have now. Either way, the search continues, the story continues. and you're part of it. Take a breath, let it settle. You've traveled 13.8 billion years in a single evening, from nothing to everything, from the first spark of existence to the present moment, where you sit quietly, listening, wondering. The universe is not separate from you. You're woven into it. Every atom in your body is a relic of cosmic history. Every thought in your mind is a ripple in the fabric of space-time. You are the universe, looking back at itself, trying to remember, trying to understand. And maybe that's the answer to the deepest question. Not why something exists instead of nothing, but why existence bothers to ask. Why matter becomes mind. Why the cosmos learns to wonder. Maybe the universe exists so that it can know itself. And in you, in every person who's ever looked up at the stars and felt awe, it does. Thank you for being here, for listening, for wondering alongside me. The story of the universe is vast and strange and beautiful, and it's not finished. New chapters are being written every day by scientists discovering exoplanets, by telescopes capturing light from the edge of time, by minds like yours asking questions that haven't been asked before. There are more stories to tell, more mysteries to explore, more quiet nights where science and wonder meet in the dark. So, rest now. Let the vastness settle softly around you. Let the strangeness of existence feel less like a puzzle and more like a gift. And when you're ready, we'll meet again, in another quiet moment, with another story, another journey through the cosmos, told softly, held gently, shared like a secret between friends. Sleep well, dream gently, and remember, you are made of stars. Good night.